Hi, it's Mr. Baker here, and today we're going to be looking at terminal velocity. So today we're going to be looking at weight and terminal velocity, and we're going to have a look at this. Heavy stuff falls faster than light stuff, right? So we're going to try and answer that question and see if that is true. And we've got some very special effects. Woo, look at that. Okay, right, so have a look at this. We've done some work on forces and motion, and so I'd like you to be able to just describe the motion of these four things, and I'll go through them with you in a second. So if you just want to pause it and just think about it or write down the answers, what do you think is going to happen in each of those four cases there? So pause it then. Okay, did you pause it? Okay, I'm going to go through the answers with you now. So here we've got an object. It's moving in that direction and it's got a force in that direction, so it's going to be accelerating down. Here it's moving in this direction, but this force and this force are equal, so there's no resultant force on it, so it's going to have a constant velocity. Here it's moving that way, moving down, and there's a larger force. We represent forces by the size of their arrows, don't we? So now this was going to be accelerating more than in the first one. And this is moving down in this direction. There's a force upwards on it, the resultant force upwards, so that would mean that this object is decelerating. Hopefully you got all of those. But wait. Okay, now we'll talk about what weight is. So this whole lesson's about weight and terminal velocity, so we better look at what weight actually means. So the stuff that's in us, the stuff that's in anything, is the mass. And that won't change no matter where I am in the universe. The amount of stuff in me is my mass. My weight is linked to my mass, but it's also linked to where I am in the universe. So when I'm on Earth, there's a gravitational pull on me, the gravity, and so I work out my weight by multiplying the amount of stuff inside me, my mass, times the acceleration due to that gravity. That gives me my weight. If I went to other places, then my weight would be different. So the force due to gravity depends on the masses of the two objects being attracted to each other. And if you remember, we know that Newton's third law says that's an action-reaction pair. There's a force pulling down because of the Earth on me, and I'm pulling up on the Earth with exactly the same weight. But it's just that, and if you look at Newton's second law, it's just that my mass is a lot less than the mass of the Earth. And so if I jumped out of a window, I would, not that I'm going to, if I jumped anywhere, then I would fall down and the Earth wouldn't fall up to me. On Earth, that force is 10 newtons per kilogram. On the Moon, it's 1/6 of this. Why do you think that is? Well, yes, you're right. It's because the Moon has got a smaller mass, and so it hasn't got the same gravitational pull. So just over 400 years ago, there was a man, I'm sure you've heard of him, Galileo Galilei. He was an Italian scientist, and around about 1590, what he did was he dropped two spheres of the same volume but different masses from the Leaning Tower of Pisa to see how stuff fell. And his idea was that as long as the volume was the same, then it wouldn't matter how heavy they were. They would drop at exactly the same rate. They would accelerate down towards Earth at exactly the same rate, which isn't intuitive at all. We all think that heavier stuff will fall faster than lighter stuff. It's just what we all think. But I'm going to prove to you that Galileo was exactly right. So, this is what I'm saying. All objects fall at the same rate. Really? That doesn't sound right. So let's prove it. So if I've got a mass of 1 kilogram and I've got another mass of 2 kilograms. So these have got the same volume, but they've got different masses. So we can work out the weight of that, can't we? We've just looked at how we can work out the weight. Weight equals mass times gravity. Now I'm going to tell you that gravity on Earth is 10 newtons per kilogram. So the weight of my 1 kilogram ball here is 1 times 10 is 10 newtons. So I've got a force of 10 newtons pulling down on this 1 kilogram, let's say it's a cannonball. What's the weight of this one? Well, 2 times 10, 20 newtons. So it's got twice as much force, so I've represented that with an arrow twice as big. So what rate will they fall? This will be their acceleration, and how do we work that out? So you would have done a lesson on Newton's second law, and you would have seen that force equals mass times acceleration. So if we want to find the acceleration, acceleration equals force divided by mass, and in our case the acceleration equals the force, which is the weight, divided by the mass. So in this case here, the acceleration is going to be 10 newtons, because that's the force that's pulling it down, divided by its mass, 1 kilogram. The acceleration is going to be 10 meters per second squared. In this one over here, the acceleration is going to be 20 newtons, because that's the force that's pulling down on this one, divided by 2 kilograms, which equals 10 meters per second squared. So they're going to accelerate down at exactly the same rate. So this is what Galileo proved, that they fall at the same rate. They both fall at 10 meters per second squared, even though their masses are different. But that's fine, as long as there aren't any other forces acting on the object apart from weight. But what other forces there in the real world? Well, yeah, air resistance. We might call it drag, might call it friction, but we've got air resistance, which would act on something that's falling on our planet. So let's see what would happen in that case. I know that if I've got a 1 kilogram object and I drop it on Earth, it will have an acceleration of 10 meters per second squared. So initially the forces are unbalanced. It's only got a force down. There isn't any other force acting on it. If I just drop that cannonball, there's nothing else acting on it apart from its weight, and it would fall. As it falls, and it goes faster, it hits into more air. The air resistance increases. The resultant downwards force becomes less, so it speeds up less quickly. So the acceleration decreases. So it has a little bit of air resistance as well. So the resultant force is less, and so it falls less at a rate less than 10 meters per second squared. So the acceleration is still accelerating downwards, but it's not accelerating as fast. At some point, the air resistance increases more and more as it's accelerating more, until the weight that's pulling down equals the air resistance, the force of the air resistance up, and so the resultant force equals 0 as those two forces cancel each other out. And when those two forces cancel each other out, there's no acceleration, and so we just have a terminal velocity, like a final velocity that's reached. It's like at the top speed of that cannonball. We call that the terminal velocity when there's no acceleration and the forces have balanced, when there is a resultant force of 0. So it would carry on moving, but it would be going at a constant speed down. Okay, and that's what terminal velocity is. So I'm going to explain that in terms of a parachute jump, and you need to be able to look at a graph to explain what's going on. So I'm going to show you this graph. Okay, so we're going to draw a velocity time graph for a parachute jump. So you can see in my amazing drawing here, we've got somebody who's just started their parachute jump. They've just jumped out of the plane and they are accelerating down. So at this point here, they've just come out. The force that's acting on them is their weight. Okay, so they've got their weight acting on them, but that's the only force that's acting on them. So they're going to be accelerating really fast. So if they're accelerating, then they'll be doing that. In fact, we know how fast they're going to be accelerating. They'll be accelerating with gravity, which would be 9.81 meters per second squared. And they'd accelerate for a while until they get to a point where there would be some air resistance. Okay, so there'd be a little bit of air resistance, and as they go faster and faster, that air resistance would increase. So their acceleration would decrease until they fell a little bit further. And now the weight that's pulling them down equals the air resistance. And so for a little bit they would fall here there's a balanced force. We know that from Newton's first law, which we've done a few lessons ago, when we've got a resultant force of 0, then there's no acceleration. The object just carries on doing what it's doing, and what it was doing before was moving, and it was moving at this speed, whatever this speed was. That's a very dodgy looking line, but we've got a line there, and that velocity there would be the terminal velocity for our parachute jumper before they pulled the parachute cord. Okay, so they're falling at this terminal velocity as they fall down because the air resistance equals their weight. Now, at a point, if they carried on doing that, they go splat, wouldn't they, on the floor? So at a point, so that they can land safely, what they do is they pull the cord of their parachute, and their parachute, how do you draw a parachute? Oh, look at that. And their parachute suddenly opens, and their weight is still the same, but now suddenly their air resistance has increased a massive amount. So there's a force going in the opposite direction to the direction they were travelling, and we know that from Newton's first law again, if we've got a force going in the opposite direction to the direction we're travelling, then we decelerate. So they would be decelerating. Over time, they're slowing down. If they're slowing down, there's going to be less air hitting into them every second. If there's less air hitting into them, that means there's less air resistance. So over time, as they fall down, the air resistance gets less and less until it matches their weight. And at that point there, they go at another terminal velocity. So now they've got a terminal velocity but it's now a slower terminal velocity, and hopefully it's a terminal velocity that is slow enough that when they actually land here they don't die. So hopefully this speed is one that actually is safe enough for them to, when they hit the ground, they stop. In fact, they would stop probably pretty quick, wouldn't they? So, like that. Okay, so let's look at the stages again. Okay, so at number 1, that's they're just coming out of the plane, they're accelerating, there's a force of weight acting down on them, but there's no other forces acting on them. At number 2, they are accelerating, but their air resistance is increasing because they're speeding up, so the air resistance is starting to get bigger and bigger and bigger. So they're accelerating, but they're accelerating slower. Until they get to number 3, where they reach a terminal velocity. Terminal velocity before they pull the parachute cord. It's a terminal velocity because the weight equals the air resistance going back up. At number 4, they pull the parachute cord, and all of a sudden they decelerate, and they're decelerating here because the air resistance is greater than their weight. And at number 6, they're going at a slower terminal velocity because as they're going slower in portion number 5, their air resistance is decreasing until it matches their weight. When it matches their weight, they're going at a slower terminal velocity, and then at number 7 they land safely so that they can jump another day. Okay, and that's it. Okay, so that's pretty much it for today's lesson. I'm just going to give you a few questions just to see what you've understood, and we'll just go through them before we finish. So have a go at these questions here. So just pause the video and see if you can answer those questions. I will go through with you those in a second. So pause it there. Have you paused it? Okay, don't cheat. Pause it. and then I'll go through the questions. Okay, right, let's go through those. So what is weight? Weight is the force on an object's mass because of gravity. Hopefully you said something like that. If weight equals mass times gravitational field strength, what is my weight if I'm 80 kilograms? Gravity is 10 newtons per kilogram on Earth, so mass times gravity, 10 times 80, 800 newtons. What is terminal velocity? So the terminal velocity, when the accelerating force is equal to drag or friction, it will have zero acceleration, and so it will reach a constant terminal velocity. How can I make my terminal velocity increase? Increase the accelerating force, have a bigger force going down, or reduce the drag or friction. And in fact, terminal velocity doesn't just happen when you've got parachute jumpers. It could also be a car or a motorbike. So if I want, I could have a terminal velocity because my engine is a certain size, or because I'm putting the throttle down a certain amount. If I increase how fast I want to go, I would try and increase the force that I'm using. I'd get a bigger engine, or put my throttle down more, and that would increase the force. So I could do it like that as well. But what you should be able to do today, we've just had a lesson on weight and terminal velocity. So you should be able to state the difference between mass and weight and describe the forces acting on an object falling through a fluid. You should be able to calculate the weight of objects and apply the concept of balance forces to being able to explain why an object falling through a fluid will reach a terminal velocity. Okay, so let's see those special effects again. Wow, that's where the budget's gone. So we've just had our lesson on weight and terminal velocity, and heavy stuff falls faster than light stuff, right? Well, maybe if there's some air resistance, that might be true, because the terminal velocities might be different for a feather and a cannonball. But if we've got the same volume of feathers and the same volume of cannonball, then they will fall at exactly the same rate no matter what their mass. And that is all down to what Galileo did, dropping stuff off the Leaning Tower of Pisa. So that is our lesson today on weight and terminal velocity. I have been Mr. Baker. Thanks very much, and I will see you next time.